Hey, fine calculus students. Today's topic is differentiability and continuity. Now let's just kind of look at that word differentiability. What that means is it's capable, a function is going to be capable of being differentiated. So differentiability, capable of being differentiated. Or another way to think about it is that a function possesses a derivative, okay, at each of the x values of that function. So possessing a derivative and capable of being differentiated. All right, so here we have a little description of differentiability. A function f is differentiable if the derivatives from the left and right exist and are equal. So we're going to do some work with regard to this description. We're going to use the alternative limit form of the derivative, and as you guys can see here, the derivative notation at a particular c value we're going to be working with. And then here we have a difference quotient, difference of two y's over a difference of two x's. So differentiability is going to fail in a couple of situations, and we're going to look at those situations in this video. Let's first look at a function, a graph that is not continuous. So looking at a particular function that we've worked with in the past, let's look at the greatest integer function. Draw a few steps, closed on the left, open on the right, stepping up. Okay, just a quick rough sketch here. Okay, so to look at the idea of differentiability, we're saying that a graph is not differentiable when it's not continuous. And kind of thinking about the definition I mentioned earlier, that differentiability can be thought of as possessing a derivative. Well, okay, if you look at these breaks in the graph, how can we have a derivative, a tangent slope at those particular breaks or points of discontinuity? So, but our work in using the alternative limit form of the derivative is going to help verify that as well. All right, let's just consider a point of discontinuity on the graph here at x equals 0. Okay, and let's set up the limit of the difference quotient here. Okay, and we want to look at the left-hand derivative. So let's look at coming to 0 from the left. And f of c in this case would be f of 0. Okay, so we're looking at the left-hand derivative. We're working with the function, the greatest integer function. So right here I'm going to insert the greatest integer function minus f of 0. Well, if you come over to the graph, f of 0, the input 0, the output 0. Okay, and so what we're going to do here is we're just kind of linger, think about evaluating this function at values close to 0 but to the left of it. So for example, negative 0.1. So we know the denominator would be negative 0.1. So what would the numerator be? Well, if I'm at negative 0.1, I'm over here. The output for the greatest integer function would have me be at negative 1. So it appears that if I'm real close to 0 to the left of 0, my outputs, my numerator over here is going to be negative 1, because that's just what the greatest integer function does. It has an output of an integer value here. So negative 0.1 becomes negative 1. Negative 1 divided by negative 0.1. If you get closer and closer to 0, you would see through a lot of different situations here that this output is approaching infinity. And right there, through our earlier work, we know that if you get infinity, that we can say that the limit does not exist. Okay, we're not leveling off to some particular L value, if you will, as we called it earlier. If I'm approaching a particular C value, okay, along the x-axis, if I'm not talking about end behavior here, then we are going to say that that limit does not exist. Okay. Let's go ahead and look at the right-hand derivative. Even though the function already fails to be differentiable because the left hand derivative does not exist, we're going to go ahead and do a little work with the right-hand derivative. Okay, and then skipping this step right here, because it's the same thing. Let's just investigate the outputs as I approach 0 from the right. Well, coming over to the graph, if I approach 0 from the right, I'm talking about 0.1. If I evaluate this at 0.1, well, if my input is 0.1, my output is 0. So that's the branch I'm on, the step I'm on. So it's 0 divided by 0.1. And if you notice, the closer you get to 0 from the right, 0.001, the greatest integer has us evaluating or getting an output of 0. So the closer we get to 0 from the right, the numerator will be 0. The denominator will be a small number, but irregardless, the output's still going to be 0. So we say that this graph is not differentiable. And the alternative limit form of the derivative helped us in our work with that. Let's look at another graph that would fit in this category. Think of a graph that has a point discontinuity. Okay, perhaps this is labeled C. This graph is not continuous at C. It's not differentiable at C. Okay, just another example of this graph failing to be differentiable. So the graph must be at least continuous for it to even be thought of as differentiable. Okay, let's look at another situation. A function is not differentiable when it has a sharp turn. When a graph has a sharp turn. And to help us understand this situation, we're going to consider an absolute value function. So we're going to take a look at differentiability. We're going to consider what's happening at x equals 2 and the behavior there at x equals 2. So let's find the left-hand derivative. So as I approach 2 from the left, difference of the y's over the difference of the x's. Okay, for the f of x, I'm going to insert the function f of 2, looking at the graph, we can quickly see that f of 2's output is 0, and my denominator is, oh, my denominator, excuse me, come back here, is x minus 2. Think about this function here that we're looking at. We've dealt quite a lot with this year and last year too. The left-hand limit. Okay, if you think about what that graph looks like, as I approach 2 from the left, the outputs are going to be -1. Okay, so that's my left-hand derivative. Let's look at a right-hand derivative. And what I'm going to do is I'm going to kind of cut all the way over to here and say, okay, well, this is the function I'm dealing with. What's the right-hand limit here? The limit from the right is going to put us, okay, on the portion of the graph whose y values are 1. So we can clearly see that even though the left-hand and the right-hand derivative exist, they're not equal. So this fails the differentiability test, so to speak. So that sharp turn doesn't allow for this graph to be differentiable. Okay, let's look at another situation where we may have a sharp turn. Could be that we're working with the piecewise graph, and perhaps the first piece that we're working with from the left is parabolic, and then the graph is continuous and it changes into a linear function, and we can clearly see that this is a sharp turn, and we'll call this C. Okay, here. So this graph is continuous, but it's not differentiable. Okay, and it has a sharp turn in this kind of situation. So it doesn't always have to be absolute value. It can certainly be something like this. And so one more case to look at. The third and final situation that we're going to look at for failing differentiability is when a graph has a vertical tangent line. When a graph has a vertical tangent line. So to help us with that, we're going to look at and consider the function, the cubic function, the cube root of x to the 1/3 power. Okay, so as we take a look at that graph, what we see is that as the graph approaches the origin, it becomes very, very steep. All right, so let's consider what's happening at x equals 0. Let's look at the left-hand derivative and the right-hand derivative. So f of x minus f of 0 over x minus 0 . Well, the function I'm working with is x to the 1/3. And the functional value at 0 is 0. And then in the denominator I have x minus 0. So kind of cleaning this up over here. Okay, we see that that's x to the 1/3 over x to the 1st. Okay, well, we can simplify that. We can subtract the exponents. So we would have 1 over x to the 2/3 power here. Okay, so spending a little time evaluating this function for values close to 0, x values close to 0 to the left of it, negative 0.01 taken to the 2/3 power, negative 0.001 taken to the 2/3 power. The denominator is becoming very, very small. It's getting smaller and smaller and smaller, and 1 divided by a very small number is going to result in a very large number. So we can see that the limit does not exist. We have a vertical tangent line there, so to speak. The slope becomes very, very steep. And the same thing holds true as you look at the right-hand derivative. So if I were to approach 0 from the right, then I'm still dealing with 1 over x to the 2/3. And what results there is that you do have infinity. So we say that this limit does not exist, as in our previous work. Okay. All right, and another example of a vertical tangent line that with the particular function that we worked very much with is the square root graph. So if we kind of take a look at perhaps this particular graph right here, we call this C. Okay, if you can kind of just look and see what's happening here. If you're interested in the slope of this curve at C, as you approach C from the right, now there is no left-hand derivative, just a right-hand derivative here. As you approach C from the right, if you were to approximate the slopes of the tangent lines by using secant slopes, you can very well see that the closer you get to C comma 0, that the secant line is very, very steep. So here's another example that would fit in this category as well. So hopefully we've looked at several situations and you're comfortable with all the different situations of when a graph fails to be differentiable. See you soon.